Welcome back, strategists. Let's dive right into this explainer, where we're going to trace exactly how the language of geometry and problem-solving evolved, from brilliant ancient minds all the way to the modern data models and investigations you absolutely need to master. Listen, if you're preparing for your Cambridge examinations, specifically syllabus codes like 0580, you know by now that mathematics isn't just about casually memorizing a bunch of formulas. It's about absolute, unshakable precision. I want you to think of your exam like a high-stakes space mission. There is literally zero margin for error. Every single calculation, every geometric proof, and every data model must be absolutely perfect for launch. In my experience, there are usually two types of students who struggle here. You've got the Alex type, right? They overload their answers with raw mathematical facts but offer zero actual analysis. And then you have the Sam type, students who rush through the paper, completely missing the specific requirements of the command words. Today, we're fixing both of those approaches. We'll be breaking down geometrical vocabulary, symmetry, modeling, and investigations to build your strategy from the ground up. We're going to make sure you have the analytical tools to tackle the most complex extended curriculum questions with total confidence. Let's get into it.
We're going to begin by grounding our strategy with Archimedes. Now, this was a thinker whose influence was actually pretty limited during his own lifetime, simply because his mathematical genius was just so far ahead of anyone else around him. When we think of Archimedes, compass in hand, we are literally looking at the foundation of modern problem solving. He lived between 287 and 212 BC, yet the intense rigor he applied to mathematics, that's the exact same rigor Cambridge examiners expect from you today. He didn't just guess, he proved his work, and that's exactly the mindset we need to adopt as we navigate through this material. No guessing, just proof.
Here is our flight plan for today. We'll start with the Greek origins, establish the language of geometry, and then explores circle and symmetry properties. From there, we'll shift to modern tools for graphing and inequalities, before applying it all to modeling physical data and investigating mathematical patterns.
Section 1. The Greek origins. So, we're starting our journey back in the Golden Age to see exactly who built the mathematical toolkit we still rely on today. Now, you might be wondering, why do I need to know about ancient history for a math exam? Well, before we jump into the complex equations and specific command words on your paper, it really helps to understand where these concepts actually came from. They weren't just invented to make your life difficult, I promise. They were developed to decode the universe itself. Look at these incredibly diverse contributions. We've got Thales, who literally invented the 365-day calendar and predicted solar eclipses. Pythagoras founded a legendary school of mathematics and was succeeded by Theano, an absolute trailblazer. Eudoxus cracked the formula for the volume of a cone, Euclid wrote a textbook so flawless it remained the standard for 2 millennia, and Apollonius gave us the names for the parabola, hyperbola, and ellipse. Every single time you calculate a volume or graph a curve, you're standing on the shoulders of these giants.
Section 2. The language of geometry.
What's really crucial here is that those ancient discoveries directly form the geometric vocabulary we use to describe our physical world today. To ace your exams, you've got to speak this language fluently. You need to instantly recognize terms like vertex, plane, perpendicular bisector, and reflex angles. Think about practical geometry in action, like sharp vertices, parallel lines, and similar geometric shapes used in massive construction projects. The impressive glass and steel structures we see in modern cities, they're nothing but physical manifestations of your geometry syllabus. When an examiner asks you to calculate an interior angle, they are asking you to apply the exact same principles that keep these huge buildings standing. There is zero margin for error in the real world and zero margin for error on your paper. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, let's talk about a classic trap that catches out so many students. You absolutely must master the difference between similar shapes, which scale up or down by a specific factor, and congruent shapes, which are exactly the same. Students like our hypothetical Alex will often write a whole paragraph throwing around both terms hoping one sticks. Don't do that. Decode the command word. If a question tells you two triangles are similar, it means their angles are identical, but their side lengths, surface areas, and volumes are scaled. If they are congruent, they are mathematical twins, perfectly identical in every single metric. Confusing these two will instantly cost you marks, so lock this definition into your strategy right now.
This is your cheat sheet. It breaks down the fundamental angle properties you need to calculate unknown variables. These are your non-negotiable rules. Angles at a point always sum to 360 degrees. On a straight line, 180. The angle sum of a triangle is 180 and a quadrilateral is 360. And for parallel lines, never forget that alternate and corresponding angles are equal.
This is where I want you to think about the Peel framework. Point, evidence, explanation, link. When you're asked to give geometric explanations in your exam, you can't just write down the final number and move on. You must explicitly state these rules as your evidence and explanation to guarantee top marks.
Section 3. Circle and symmetry properties. Moving up from straight lines and basic polygons, let's step firmly into the extended curriculum and look at the symmetries governing circles. This is high-level spatial reasoning. We're going to step through these essential circle theorems, which are absolutely critical for giving geometric explanations. First, the angle in a semicircle is always exactly 90 degrees. Second, the angle between a tangent and a radius, also 90 degrees. Third, if you have a cyclic quadrilateral, meaning all 4 vertices touch the circumference, its opposite angles will always sum to 180 degrees. And finally, you have to know how to apply the alternate segment theorem. When you look at a circle with intersecting lines on your exam paper, your brain needs to immediately run through this exact checklist. And right here, we see the inherent perfect symmetry of a circle. Equal chords are always equidistant from the center, and the perpendicular bisector of a chord will always pass right through that center point. These symmetry properties are incredibly elegant, and honestly, they're your secret weapons for unlocking those complex multi-mark questions. Now, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 4. Graphing and inequalities. All right, next we're shifting from pure geometry into modern technological applications. While the Greeks had to do everything by hand with a compass and a straight edge, we get to use graphic display calculators to visualize abstract concepts instantly. Notice how this tool actively shades the appropriate region for a linear inequality. Whether you're using a calculator in class or sketching this out manually under exam conditions, the core process doesn't change. You identify your boundary line, figure out if it needs to be solid or dashed based on the inequality, and then test a coordinate to shade the exact correct region. It's a systematic process.
Now, let's do a quick find the flaw comparison. Look at the difference in complexity here. Finding the gradient and y-intercept of a basic line like y equals 2x plus 3 is straightforward. The gradient is 2, the intercept is 3. Easy. But compare that to finding the perpendicular bisector between 2 exact coordinates, like p at 1,12 and q at 5,2. This is where students like Sam rush and lose massive points. It's a multi-stage mission. First, you need the midpoint of p and q. Then, you calculate the gradient of the line connecting them. Then, and this is the part people miss, you have to find the negative reciprocal of that gradient to get your perpendicular slope. Finally, you substitute it all into the equation of a line. You cannot rush this. Every step must be executed flawlessly.
Section 5. Modeling physical data. So the crucial point of this next section is applying our math to accurately model real-world physical behavior. Math isn't just numbers floating on a page. It's the framework we use to understand physical science. Take a look at this data scan challenge. We've got a spring, and as we add mass in grams, we measure the extension in centimeters. At 50 grams, it stretches 3.1 centimeters. By 500 grams, it's at 31.2 centimeters. What's the core trend here? It's an approximate linear relationship. As the mass increases, the extension increases proportionally. If you plotted this out, you draw a line of best fit, find its equation, and boom, you have a working mathematical model. You could use it to predict the stretch for 275 grams without even testing it. That's the power of modeling.
But here is the critical, real-world question you need to ask yourself. What happens to our model and the actual physical spring if a 5-kilogram weight is suddenly dropped onto it? Our model works beautifully from 50 to 500 grams, but 5 kilograms is 5,000 grams. If you just blindly plug 5,000 into your linear equation, your calculator will spit out a massive extension length. But does that make any real-world sense?
Absolutely not. And this is a massive exam takeaway. Every mathematical model has a specific range of validity. A 5-kilogram weight wouldn't just stretch that delicate spring, it would permanently deform it or snap it right in half. The physical reality completely overrides the mathematical equation. The system breaks down. Always check the real-world logic of your mathematical answers.
Section 6. Investigating mathematical patterns.
Let's move to our final section and see how all of this builds into solving logical, sequential puzzles. In the Cambridge syllabus, investigations require you to systematically track variables. Take this treasure chest investigation.
Imagine a game with 12 chests, and we're eliminating them round by round. In round 1, the odd-numbered chests are discounted. 1, 3, 5, 7, 9, and 11 are gone. In round 2, we continue the alternating pattern with the remaining chests, discounting 2, 6, and 10. By round 3, chests 4 and 12 are removed. Following this strict sequence of elimination, the sole survivor, the winning chest, is chest 8. But the true test of your exam strategy comes when the parameters change. What if there are 4, 5, 8, 9, or 15 contestants? Your job is to carefully run the simulation for these new numbers and log your results into an ordered table. You're trying to identify the underlying numerical pattern, because once you spot that pattern, you don't have to manually cross out numbers anymore. You can instantly predict the winning chest for massive scenarios, like 31, 32, or 33 contestants. It's all about moving from manual counting to identifying the mathematical rule. I'm going to leave you with this final, provocative challenge to test your analytical skills. What is the ultimate algebraic rule linking the winning chess X and the number of contestants N? How do you turn that pattern into an unbreakable law? That's what gets you to 100% mark potential. Listen, students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing right now. Our team responds to absolutely every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.